So we've already seen how to solve some inequalities and how they're similar to solving equations. The only thing we're really changing in 3.4 is we're taking multiple steps to solve those, just like we did with equations from earlier. So if you want to look through that first question, I have my solution underneath, which kind of introduces this section. But basically what this idea is talking about is we can model situations using different kinds of inequalities. So the one up here where we're selling t-shirts for $7.50 each, I have $7.50 times x for the number of shirts, plus the $337.50 that we already have has to be at least 500 for our goal. So that kind of inequality, we're going to take a couple steps to solve it, because again, it's a little bit more complex than the ones from earlier. So we'll learn how to write those and solve those in 3.4. So we can solve our multiple step inequality the same way we'd solve anything with one step. So it's still using those properties of inequality. Remember, those are just adding, subtracting, multiplying, dividing. Because we're going to transform those into series of simpler equivalent inequalities. So a lot of what we've been using before, just with a few more steps. So trying those practice ones, and we'll see what those look like when we solve it. If I have a question like part A here, if I have negative 6a minus 7 is less than or equal to 17, first thing, just like an equation, is you'd want to get rid of everything besides your variable term on one side. So if I want to isolate the a, I got to add 7 first. I get negative 6a is less than or equal to 24. Notice no sign change. But then here we have to remember that when I divide or multiply by a negative, so if I divide it by negative 6, I get negative 4 first of all, so positive divided by negative is negative, but I also got to make sure I switch the sign. And it also asks us to check, which just means that we have to plug in this negative 4. If I substitute, I find that 17 works because that's equal to 17. And then if I want to try something greater than negative 4, I can just use something like negative 3. So if I plug in something greater, I see that it also works because 11 is also less than or equal to 17. So same thing with these other examples. Again, just got to start off by isolating the variable. I want to subtract 5 first, then divide by negative 3. Again, remember that if my variable's on the right, I still have to switch signs when I divide by negative, but then if I want to rewrite with the variable on the left, make that easier to graph, I also got to make sure I switch that sign back. So it actually kind of switches twice if we move that variable over. And again, we have our check to make sure some values work. So 3 doesn't work because it's not it's not greater than negative 4. But if I plug something in that's less than 3, so if I substituted 2, that does work because negative 1 is greater than negative 4. So last one, same idea. If I subtract 30 first, I want to isolate my x. So I subtract my 30, divide by 0.8. Remember, this time I don't have to switch the sign because I divided by a positive number. So I get x is less than 25, which I can again rewrite with the variable on the left if we want. And I can plug something in to check. If I plug in 25, I get that my answer is 50. So 50 is not less than 50, but if I plug in something less than 25, so if I plug in 0, 30 is less than 50, so that does work. So something that we can also do with these is I can adapt some familiar formulas to write those inequalities. And to use real-world situations, we're going to have to do that to figure out which symbol we're using. So in this first situation, we want to make a rectangular sign, first of all, that is 18 feet long. We have no more than 48 feet of trim. So again, the no more than part is suggesting an inequality. And the trim, we kind of also have to think what that means because we have to get the possible widths. So if you're thinking trim on a sign, again, trim would be like the parts around the outside. So if we're describing the part around the outside of a sign, part on the outside is going to be perimeter. So I wrote my perimeter formula down. It's twice the length plus twice the width. We also know some things from the question. We want the length to be 18. We know we have 48 feet to work with for the trim, so that should be my total perimeter. And we also know possible widths, so we're looking for width. So notice that we said we have no more than 48 feet. That means we don't have to use all of it, which means I can adjust my formula slightly to read the perimeter is got to be greater than or equal to the length and the width put together. So whatever length and width that I choose, it can be up to and including 48, but it can't go over. So I need less than or equal to. So if I just plug in what I know so far, I know the length should be 18. I know I have 48 feet to work with. So now if I plug those in, I get 36 plus 2w is less than or equal to 48. Now I'm just taking my steps to isolate w. So subtract 36, divide by 2, and we should get my width has to be less than or equal to 6. So that means we have at most 6 feet to work with. Anything bigger than that would make my inequality not true. So let's go ahead and try that with some more. If I want to find the solutions here, this time I have 15 less than or equal to 5 minus 2, and then parentheses 4m plus 7. Again, whenever I have parentheses, that means I want to distribute the number on the outside. So my first step is taking that negative 2 and multiplying it times the first term and the second term inside the parentheses. Then if I simplify, negative 2 times 4, negative 8, negative 2 times 7, negative 14. We also want to remember here too is that we want to combine like terms first. So if I have a 5 and a negative 14, 5 minus 14 comes out to negative 9. So I subtract those first. And then continuing our inequality over here, I want to isolate my m term. So let's add 9 to both sides and divide by negative 8. Remember that division step by a negative, we have to flip our sign. And then if we want to write that variable again on the left-hand side, we have to flip the sign back. So if you want your variable on the left, you might have to flip twice, but remember every time we divide or multiply by a negative, that sign has to flip at least once. And then for our check here, because it asks us to check our solutions, first of all, you can plug in negative 3. So if I plug negative 3 into the right side of this inequality, that eventually comes out to be 15. So since 15 is what all this simplifies to, that's greater than or equal to 15, so that does work. And then again, since our variable just says it has to be less than or equal to negative 3, if I plug in negative 4, that's less than negative 3. So if I plug that in and simplify, I get 23. And 23 on the right-hand side is greater than or equal to 15, so that would also work. So some inequalities will have variables on both sides of my inequality. As to now, we've just seen it with one so far. We need to gather the variable terms on one side of the inequality and the constant terms on the other. And actually, it doesn't matter which side you choose. But usually what I do is I try to keep things positive. So in this first example, 3b plus 12 is greater than 27 minus 2b. First thing you can do is add 2b to both sides, because I can choose to move all my variable terms over to the left and cancel out anything on the right. So after I've moved those to the left and I get 5b plus 12, I want to get rid of my constant terms from the left-hand side and move them over here. So subtract 12 on both, and I get just 5b, which is what I wanted. Variables isolated on the left. 27 minus 12 would be 15. Last step is to divide by 5. And remember, we're not switching the sign because we divided by a positive. So b would be greater than 3. Remembering to check our solutions, if I plug in 3, it's 21 and 21 on both sides, so that doesn't work. So if I plug in anything bigger than 3, I think I plugged in 10 for both of these, that means that our original works. So if I plug in 3, this side is bigger than the side on the right. 42 is bigger than 7. So we can also say instead of adding 2b to each side to start, just like we did in that last practice question, we could actually treat those first two steps kind of interchangeably. So you could have also chosen to subtract 12 before you started, before you add 2b. You just can think that we can do those two steps in any order. So it doesn't matter if you add the variable terms first or deal with the constant terms, we just have to do one and then the other. So last little step in here is that sometimes we have an inequality that results in something that's always true. So 4 greater than 1, that's always true. In that case, we say our solutions are just any real numbers, so all real numbers would be the answer. Kind of think back to your infinite solutions. If the statement is never true, so something like 9 less than negative 5, because that can never work, then the inequality has no solution. So we've seen cases like this before. So first case, if I try to isolate my terms here, I can subtract 5n from both sides, but what that happens is it's just going to cancel on both sides. So if I have 9 is less than negative 1, that's not true, so that's going to be no solution. 9 cannot be less than or equal to negative 1. So other example, if I first combine my like terms, 7x minus x would make 6x. Then if I try to gather my variable terms, I subtract 6x on both sides. It cancels on both, so I'm just left with 8 is greater than or equal to 2. And since 8 is always greater than 2, I'm left with all real numbers as my answer, because that will always be true. So also adding in our 3, 6. So 3, 6 is kind of taking this idea and expanding on it a bit more on both sides. So we have something called compound inequalities. So I'm going to skip past this first question for now. We might be able to look at it back in class, but it's going to involve a value that's between two numbers because we have a lowest and highest value that we could get from that tree. You can use a compound inequality to represent that relationship. Compound inequality consists of two distinct inequalities, and it's going to be joined by one of these two words. It's going to use and, or it's going to use or. So you always see one of those two. We can find the solutions of our compound inequality either by identifying where the solution sets overlap or by combining the solution sets to form a bigger one. And that kind of depends on what kind of inequality you're looking at. So our first type over here that we see on the left is where you use the word and. So and is going to be your overlapping graph. So I have and where x is greater than or equal to 3. That's going to go off to the right this way. X is less than or equal to 7. So it starts here, goes off to the left. But if I want it to be and, I need them to both work. So I take this region in here. Notice I cut it off at 3 for the lower end and 7 for the upper end. And this is the region where they're both shaded. So from 3 to 7 is where both of these are true. X is greater than or equal to 3 and it's less than or equal to 7. So OR is just basically the opposite. I'm not looking for the overlap. I'm looking for where each graph can go. So first case, if I have x is less than -2, I start at -2 and go off to the left with an open circle. X greater than or equal to 1, I start at 1 with a closed circle and go off to the right for greater than. But then when I'm using OR, notice there's no overlap in between here. So I still separated where these two both start and stop. But OR just means we include everything. So I include the part that goes to the left and I include the part that goes to the right because it can be either or. X is less than -2 or it's greater than or equal to 1. So expanding on that a bit with some more terminology, we can rewrite a compound inequality that uses and as a single inequality. So this doesn't actually work when you're using or. So for instance, if I have those two inequalities from the last page, x greater than or equal to 3 and x less than or equal to 7, I can combine those because x is going to have to be in between those. It's got to be bigger than or equal to 3 and less than or equal to 7. So I read this as x is greater than or equal to 3 and less than or equal to 7. Another way to read it is x is between 3 and 7 inclusive. So in this case, inclusive is going to stand for the solutions of the inequality include both 3 and 7. And again, what that's going to mean is you're going to see that equal to sign underneath. So not just the less than, we have less than or equal to. So in these couple examples, we're going to see the difference between those and or compound inequalities. So if I'm looking for all real solutions that are greater than or equal to -4, again, this part would look just like this if I wrote it out by itself. But then we have and less than 6. So both parts are important. We have the first inequality, we have and we have the second inequality. So if I combine those, again, you could write them separate. We could write x is greater than or equal to -4 and x is less than 6. But if I want to write those as a compound inequality and I can combine it since it uses the word and, I can just throw both parts in there. So -4 has got to be the lowest I can go, x is in between, and 6 is the highest because it's got to be less than 6. If I was to graph that, we just kind of stick both graphs together. So -4 is the lowest, that's filled in because it can be equal to, and then all my x's can go all the way up to 6 where it stops with an open circle. So it's got to be less than 6. So it's just kind of the opposite if you're using or. Less than or equal to 2.5 means that that's basically my lower boundary. So x can be less than or equal to 2.5, or it can be greater than 6. So x can be greater than 6. So if I'm using the word or, notice there actually wouldn't be any overlap here if we're going from 2.5 and going off to the left. You can kind of see that on my graph. Or greater than 6, there's no region where they are combined, but since it's or, that doesn't matter. We just use both parts. X is less than or equal to 2.5, or x is greater than 6. And we can just state that word or in between there. So if I want to say the difference also, if I had those two phrases, x is between -5 and 7, or if I put x is between -5 and 7 inclusive, remember the only thing inclusive does is it adds in those equal to signs because I can be at my endpoints, -5 and 7. So my solution of a compound inequality involving and is any number that makes both of those inequalities true. So one of those ways I can find it is by separating it into two inequalities. And we'll actually work on these last couple problems in class. As long as you have the start of these notes done, we're just going to continue this where we left off to see some more specific examples. So make sure you come in with these, make sure you come in with questions, and we'll get this covered.